This program is a presentation of UCTV for educational and non-commercial use only. Check out our YouTube original channel, UCTV Prime, at youtube.com/UCTV Prime. Subscribe today to get new programs every week.
Fantastic days in Berkeley, wonderful weather. Some people would prefer to be out getting a suntan, and others here would prefer to come and get ridiculous. John, thank you very much for your first very entertaining lecture. Before we start, I would like to acknowledge the support of the graduate division, Vice Chancellor for Research, Joe Cerny, and his staff who have worked so hard to help put this event on to make it a success. In particular, I would like to thank Teresa Malongo, who has worked so hard on all the details and played a very important part. So, Teresa, thank you very much. So we're very pleased to welcome each of you to the second in the Hitchcock Lecture Series for Spring '96. And without further ado, I'll present John Conway, Princeton University. He's going to tell us about Fractran, a ridiculous logical language. Okay.
So, you know, there's this problem which I call the collapse problem, although other people claim to have invented it. It's sometimes called the n problem. You take n to, well, n over 2, if you can, if that's an integer, in other words, if n is even, and to the n plus 1. So you divide by 2 if you can, and otherwise you multiply by 3 and add 1. So the problem is, what happens? Well, when you look at this, you find, well, let's just have a random number. Let's just take 7. No, well, 27 is the one you should be shouting. 7 goes to 22, goes to 11, I can halve that, goes to 34, I multiply by 3 and add 1, but then I can halve that. Multiply by 3 and add 1, but then I can halve that, then I can halve that. Then I can multiply by 3 and add 1, but that now I can halve a few times, but then I can multiply by 3 and add 1. Ooh, that was quite interesting, wasn't it? Then, of course, I can't halve that, but I can multiply by 3 and add 1, but if I do, it just takes me back to 4 again. So this number has me eventually, I get down to 421, 421, 421. Well, if I took 27, I go to 82, 41, 124, 62, 31, 94, 47, 42, 71, dot, dot, dot. After some time, it gets to 9,232. But then, that was its sort of high point. After some time, some further time, it eventually gets down to 4, then 2, then 1, and so on. And every integer that anybody's ever tried has eventually got down to 1. I don't know how far people have tried it nowadays. Every now and then you see outrageous reports with tremendously large numbers in them, and I don't believe those for one moment. But certainly, the layman's did it out to 4 times 10 to the 9, which presumably therefore got past 10 to the 10 by now. Might have reached 10 to the 12, might not have done. Anyway, there's a real interesting question about this sort of game, which is, you know, does everything reach 1 in this game? Very probably it does, because if you think about this for a moment, you see that there are statistical reasons that make it seem very likely that everything gets to 1 in this game. On the other hand, showing that the statistics is really relevant, you know, the sort of empirical model that you can treat things as if they were random, is going to be very hard, and I don't think there's much hope of, you know, I don't really expect to see a solution of this problem in my lifetime. So let's just ask, let me just write the question down, does every n go to 1 in there? But as usual, when you can't solve a problem, you can ask a more general problem. I mean, you see, we notice that this number here was a half n plus 0, and you use that if n was congruent to 0 mod 2. And here, otherwise, you use 3n plus 1, which you used if n was congruent to 1 mod 2. Now, suppose instead you took n to a I n plus bi if n is congruent to I mod some number p. So in this case, p is 2, and there are essentially 2 values of I. Namely, everything is 0 or 1 mod 2, so you only need to specify 2 linear functions, which will make a half n and 3n plus 1. Suppose you do that, then can we discuss that general class of games and say anything about them? Well, we can. It follows from the kind of arguments I'm going to present today, very easily, that in general these questions are undecidable. That you can actually make any mathematical question into one of these, any reasonably well formulated mathematical question into one of those. But I think I'm going to start off by not sort of proving that general thing, but by writing my particular 14 fractions on the board. I've got to be so adept at this that I can write them in any order you like now. Sorry. So it's cheaper to write the denominators first and then the numerators, because it economizes. That's like 77, 29, 23, another 77, and the 78. Okay, so these are fractions that I think particularly interesting. I hope eventually to sort of master this method of covering the blackboard, so you sort of wander through what eventually appears as a connected segment of prose that's all written backwards. So let me just tell you this game. This is the game I call prime game. And well, it's all a very interesting game to play, but anyway, here's what you do. You start with 2, and then always, let's say, and from then on, always multiply by the earliest of the above, that's to say of A all the way through N, that gives an integral answer. So, I'm not telling you just yet why you do this. Your job is just to do it. So we start with 2. Now, we ask which of these fractions gives a whole number answer when you multiply it by 2. Well, obviously, the denominator we better divide 2, and we sort of walk along here, and not very many of them seem to divide it up, but this one does. And this is the first one. So at our first step, we'll multiply by n and get 15. Now, you know, it's handy to write out what they are in factored form. In fact, after a time, it's only sensible to write them in factored form. So now, which denominators divide 15? Well, you know, I'll let you into a secret. Most of these have a big denominator, a big prime in the denominator. A big prime means 11 or more, 2 digits. You see, this has 13, 17, 17, 19, 11, 29, 23, 19, 17, 13, 11. They all have big primes. And so, usually there's a big prime around, but in this case there isn't. But that helps us enormously in finding out what's what. Here there isn't a big prime, so we've got to go right to one of these three, and neither of these divides 15, but this one does. So we'll find ourselves using n, getting 3 times 5 squared times 11. Incidentally, I remarked that it's a nice theorem of mathematics that if any number is an integer, then so is 55 times it. And that means that there's always a fraction that works. Because if none of the other fractions work, then n will work. Okay. So here you see, if we're to use one of the earlier fractions with a big prime in it, that big prime had better be 11. There's only one big prime in this number. So we just look for the denominators to do, there it is. And we can use it because 33 is 3 times 11, and we have that. So we'll use e now and get 5 squared times 29. And now the big prime's got to be 29. Whoosh! F will be our answer. Anyway, I hope you've got the what you haven't got is the point, I trust. So I'm going to write the sort of stage numbers down here. And now what you're required to do is watch for powers of 2. Well, let's just pretend that we're going to do this. In fact, at stage 19, you get a power of 2, you get 2 squared. And some of you might like to just sort of check that for. Powers of 2 become sufficiently rare in this game that whenever they do happen, you sort of find you want to take a little photograph of it so you can show it to your grandchildren with whom you found it sometime. So let's, I'll indicate that by putting a box around there. That's my snapshot of 2. The next power of 2 you'll see is 2 cubed, which happens at stage 69. Then I've forgotten the stage numbers. 200 and something is the next power of 2. For some reason, this misses out 2 to the 4th. And the powers of 2 that you get are rather restricted. The next one's 2 to the 7th, and 2 to the 11th, 2 to the 13th, 2 to the 17th, 2 to the 19th. And the answer is, the powers of 2 that happen are precisely the ones with prime exponent, okay? So let's say they are just the ones with prime exponent in order of magnitude. Now, there is a question really about whether you count 1 as a prime. I don't count 1 as a prime, and so I didn't put the snapshot around there. So let's just say, watch for the later powers of 2, because that's the one that we actually start with. And then they're precisely the ones with prime exponent. Now this is a sufficiently intriguing theorem that I think my best way to proceed is just to prove this theorem as if it were the only theorem I'm going to prove. And then, of course, it might turn out that it is the only theorem I'm going to prove, or I might have time to say something else. Okay. Well, the proof, then. only it's not terribly clear that this is going to turn up with a proof. The proof is going to be to start with 5 to the n, 7 to the d, 13. And let me just let you into a little bit of the secret. This thing will do other things besides list prime numbers, okay? And one of the things it will do is ask, does d divide n? To ask if d divides n starts at 5 to the n. So if you have a number d and a number n and you want to see whether d divides n, just feed that number into this game and watch what happens. And I'm going to have little comments down here. I'm going to suppose that n is qd plus r, where q is the quotient and r is the remainder on division by d. So I think I better suppose that n is bigger than d greater than or equals 1. Not n greater than or equals d greater than or equals 1 is better. But in fact, I'll probably suppose that n is a lot bigger than d. I'm not really supposing this. It's just that it helps to have your ideas fixed a little bit. N is probably going to be a lot bigger than d. And r will, of course, be less than d. Okay. So let's watch what happens of this number. What's the first fraction we'll use? Well, the answer is A, because we've got to choose one for which the big prime is 13. Now, lots of you probably thought that 91 was prime. Well, in fact, you're near the truth there. 91 is actually the first number that looks prime but isn't. Since this is an important theorem and a discovery that I'm very proud of, I'll give you the proof of it. You see, if a number is divisible by 2, 3, or 5, it doesn't even look prime. Okay? So 91 at least evades that test. But then, so it follows that if a number looks prime but isn't, it must be made out of 7s and 11s and 13s and higher. Okay? Now, 7 7s are 49, and that looks square, and they're 42 prime. And 7 11s are 77, and that doesn't look prime either. But 7 13s are 91, and on the diagonal there we have a number that's much bigger, so there's the end of the proof. So we will in fact use A first. And because we have a 7, d is positive here, let's have d greater than 0. We have a 7 and we have a 13. Now when we've used A, we'll get a 17, okay? And so what's the first of our fractions has a 17 in the denominator? The answer is B. And we'll be able to use B because we have a 5. 8 5 is 5 17s. And so I think I want a little comment. What is AB? AB is 17 over 7 times 13, and then 78 is 2 times 3 times 13, and 85 is 5 times 17. And we can cross off that and that, and then we can cross off that and that. So A times B is 2 times 3 over 5 times 7. So every time we use an A and a B, we'll rub off a 5 and a 7 and stick in the 2 and the 3. So we will in fact be able to do that D times. You see, we have D7s and we have D5s because n is bigger than D. So we'll be able to do that D times. And after we've done it, we'll have replaced D5s and 7s by D2s and 3s. And so we'll be there. We'll have rubbed off the D7s, that's all of them. We'll have rubbed off D of the N5s. Okay. But then after that, we'll have a 13, but no 7. And what do we do? I'm going to go all the way along to J then. And if we do J, all it will do is change a 13 to an 11. And that's why I wrote this 13 rather faintly, because I knew it was going to change it. Now what are we going to do? We have, our big prime is 11, the first thing that involves an 11 is E, and that will convert it to a 29 when we'll use F. And so obviously we'll be applying EF a few times. Now let's have a little comment that EF is, what was it? 29 over 33 times 77 over 29. It's sort of very easy to see that cancels to 7 over 3. So every time you do EF, you'll just replace a 3 by a 7. So we'll be able to do it D times. And then we'll get 2 to the D, 5 to the N minus D, 7 to the D, 11. And then we'll have an 11 with no 3, which means K will be what we use. And that will convert that 11 into a 13. And now you know, we're in very much the same sort of situation we were at the start, except that we have a lot of 2's. But we never made use of the twoishness of the denominator in any of our arguments. So, as far as we're concerned, we have the same thing. If n is very much bigger than d, so it's so much bigger that n minus d is still at least d, then we'll apply a, b, d times followed by j, just as we did before, and that will convert d5s and d7s into d2s and d3s. And then we'll have 5 to the n minus 2d. And then that 13 will get changed to an 11. And then we'll find ourselves doing EF to the dk, which will just convert the 3's back to 7's. 2 to the 2d, 3, no 3's, 5 to the n minus 2d, 7 to the d, 13. Well, you know, after a lot of these, we'll be at a situation where at 2 to the qd, 5 to the n minus qd, 7 to the d, 13. We do that whole sort of, this block of moves q times, and that's as many d's as you can subtract from n. So let's suppose we're here. Then, what will happen now? Well, you know, qd is n minus r, and n minus qd is r. And now r is smaller than d, so we only have r 5s and 7s, so we'll only be able to apply ab r times. And what will that do for us? It'll rub out r 5s and 7s and replace them by 2's and 3's. So we get 2 to the n, 3 to the r, 5 to the 0 now, because it was 5 to the r and we broke out, 7 to the d minus r, 13. But then we'll d minus r is still positive, so we still have a 7, so we'll still be able to apply a. And a will rub out a 7 and a 13, rub out a 7, rub out a 13, and replace them by a 17. Okay? And now what happens? Well, I'm glad you asked. The prime is now 17, but we haven't got a 13. But we might have a 3. 3 17s is 51. So if r is positive, we'll use C. And then what will happen is we'll rub out a 3 and a 17. So we'll get 2 to the n, 3 to the r minus 1. And we'll stick in a 7. 7 to the d minus r. What is it now? 11. Okay. Well, you know, I think I'll continue this branch of the tree, supposing that r was positive, because it's very easy to see what happens. Now we've got an 11, and, you know, when our big prime was 11, we started doing EF as many times as we had P's. So we'll find ourselves doing EF r minus 1 times, and then K, and that'll convert all of these to the 7's. So we get 2 to the n, 7 to the d minus 1, 11 gets changed to a 13. Hope I've got that right. And then what happens in that? We find ourselves applying. Something's happened to the 5s here. Just a little bit uncertain as what's happened. Oh yes, they got created by. What actually happens here? I'm sorry, I just went a bit wrong. Let me just pause it. It never looks like this normally, so I must have just cheated. A's and B's. But let me, I tell you what, let me not worry too much about that, and let me go down to what happens if R equals 0. Well, I just sort of practically think what's supposed to go on. If R is 0, then we can't use that 51, which is 3 17s, and we have to use capital I, which just drops out to 17. So we just get to that, except that R is 0, so it's 2 to the n, 7 to the d minus 1, period. Okay. Well, I thought I was going to be able to think and talk at the same time, but I'm not. So if R is positive, we do that, then we find ourselves E-acting, which does that. Okay. And now what happens? We rub out a EF. We should be rubbing out. No, sorry. There's something that's gone seriously wrong here, and I'm just very positive about this. We're supposed to end up. Oh, I know what happened, I think. Do I? No. No idea what happened. Oh, yes, I know what I've done wrong. Yes, I got C wrong. I've got to work out what C actually is. It's 19. Okay, that's great. That's fantastic. Great. Oh, fantastic. Okay. Oh, well, the appropriate neuron must have died then. I've been remembering that for ages and never got it wrong before.
Don't you need to fix the 7s?
Sorry?
Don't you need to fix the 7s?
Oh, yes, I do. So it's d minus r minus 1 still. Thank you. Okay. Now let's see what happens. 19. Oh, yes, we'll use D here, which is, that denominator of D is 2 19s, followed by G. So we have another little comment that DG is 5 over 2, and so if we apply DG n times, it'll convert all the 2's to 5's. So we'll get 3 to the r minus 1, 5 to the n, 7 to the d minus r minus 1, 19. And now what will happen? After that, I'll have a 19 but no 2, and I'll find myself using H, which will add 1 onto the 7's, rub out the 19, plus an 11 there. Good. And that was H. Good. Got just enough room. Blackboard management. Of course, I've spent some time. Because here we'll just find ourselves doing EF so many times K, which will just convert these 3's into 7's. And so we'll get 5 to the n, 7 to the d minus 1, 13. Now, the nice thing is that this is suspiciously like this number here. Not exactly the same, but sort of closely related. Now let me show you, I wonder if it's possible to move this. It is, but it's also in great danger that everything will suddenly switch off. Lens more action. Oh, I see, look, there's a hole in the floor there, it can't move much. You know, I was once giving a lecture in Durham in England, and there was one of these enormous TV sets on a sort of, it had a three-legged thing down there, and then a pole about 8 feet high. And then it went up to a big TV set that was, you know, sort of this way. And I sort of came over to this side as I was doing something, and this started to heat up. And I didn't know what was happening at all, because I was looking at the blackboard or something. And somebody very quick-witted got up from the front and ran about 10 to 15 feet and grabbed this thing. Anyway, what do we do when we've only got 2s and 7s? Well, now there isn't a big prime. So what happens is, we'll use either L or N for a time. And it doesn't really matter which we use. They both go back to 2 and stick in a 3 and a 5. So we do that n times, and we'll get 3 to the n, 5 to the n. Okay? And if there was a 7 there, you rub it out as well. And in fact, there are fewer 7s than there were 2s. So eventually you will have rubbed out all the 7s. We don't need to analyze it in any great detail. Then after that, we can't use L or N, so we have to use N. And that will add 1, 5 and an 11. And then we're back into this EF to the something K, which just replaces the 3s by 7s and the 11 by 13. Okay. So just in case there's still somebody who can't see that right-hand side, let me summarize the entire thing in the middle here. We had 5 to the n, 7 to the d, 13, and it went to either 5 to the n, 7 to the d minus 1, 13, or 5 to the n plus 1, 7 to the n, 13. And this was what it did if r was positive, and this is what it did if r was 0. Okay. So if you sort of watch it action in enough detail, of course r equals 0 is what happens when d divides n. So you can ask which way it goes of these two and see whether d divides n or not, if that happened to be the thing that was interesting to you. But let's actually imagine what does happen with this game. If we started off at, say, I'm going to rub out some of the middle of this now, so that I have some, right. Let's suppose we start this off at 5 to the 99, 7 to the 67, 13. Suppose we started it there, what would happen? Well, 67 doesn't divide 99, so it would take what I'll call the high road, and it would come back with its next question, whether 66 divided 99. Well, that's just about as silly a question. After that, it would ask whether 65 divided 99. And so on. And it would go on asking these questions until it got to the question whether 33 divides 99. And then the answer would be, yes, it does. And so we come instead to this thing here. Now, what's that? N is 99, so this is 5 to the 100, 7 to the 99, 13. So now it's asking whether 99 divides 100. Well, no, it doesn't. Does 98 divide 100? No. 97? No. Oh, but 50 does. And so it would work its way slowly and steadily down to 50, and then it would reset to 101, 7 to the 100, 13. Now it would ask, does 99 divide 101, 98, etc. And you wouldn't get the yes answer until it got all the way down to this last question, does 1 divide 101, to which the answer is yes. Okay, now let's ask, of all the numbers that were on this board, most of which I've rubbed off, which ones of them have a ghost of a chance of being powers of 2? Okay? Well, most of them have no chance at all because they're divisible by things like 11 or 13. And there aren't many powers of 2 of that part. But this one down here does have a chance of being a power of 2, and in fact it's the only one that does. Okay? And when is it a power of 2? Precisely when d is 1. Okay? This is the only one that has a hope of being a power of 2, and it is a power of 2 when d is 1. So just before it got to here, it would actually produce the number 2 to the 101, 7 to the 0, which is 2 to the 100. So I hope you can see now how this works. It's really not a prime finder at all. What it does is for each integer in turn, it finds the largest proper divisor of that integer. Okay? And then it outputs, as it were. This is really the output state. And the output is 2 to the n, where n is the integer we're talking about, 7 to the d minus 1, where d is that proper divisor. And that's a power of 2 just if the largest proper divisor of n is 1, which is to say just if n is prime. Okay, so, well, there's that proof. It doesn't sort of tell you too much, I hope. But it does at least prove that this list of 14 fractions has the property I said it has. Okay? It basically computes prime numbers. And now I want to introduce you to Fractran, which is my improvement on Fortran. And it's supposed to convey the same sort of flavor of a slightly archaic or something computer language. So Fractran is a logician's computer language, and what you do is you have, it consists of a number of programs. Here's a Fractran program. And typically it has a number of things which are called program lines, and line P might say 2 over 5 go to Q, comma, 3 over 7, it possibly says else, 3 over 7 go to R, else 1 over 2 go to P, else stop. Except that every line has that form, and so we normally just abbreviate this until it says 2/5 go to Q, 3/7 go to R, 1/2 go to P. Okay, and let me tell you what it means. And then you see you have line Q and line R, which say similarly boring things. 4/5 go to R. So that's what a Fractran program looks like. Every one of its lines has this same sort of form. You've learned completely the syntax of a Fractran program. And now I'm going to tell you the semantics. In fact, one of the interesting things about this is that the syntax and semantics of Fractran programs are so simple that you really can learn them very quickly. So in the semantics, what you do is you have a working integer. So means replace, well, let's say if at line P, replace your working integer. At any time, the contents of your sort of store in a Fractran program consists of just one integer, okay? Which is called working integer n. And what the meaning of this is, you replace n by 2/5 of n, if that's an integer. Let's say if this is an integer, else 3/7 of n, if that's an integer, else n over 2, if that's an integer, else you stop. Okay? So what you do, the list of fractions just tells you that you are to replace your working integer by that fractional multiple of it, provided that gives you an integer. And you take the first one that gives you an integer, if there is one, and then, of course, under these circumstances, you go to line Q. In these circumstances, you go to R. And in these circumstances, you go to P, and so on. So you multiply by the first of these fractions you can, and then you jump to the appropriate line, and that tells you what list of fractions to choose next. So that's a Fractran program. And now I'm going to sort of start by showing you how to program in Fractran. But I think first I'll show you what the sort of flowchart I normally use. So you have a node for each line, P, and then you have a line here marked with 2/5 going to Q, and that's got a single arrowhead on it. And then you have another line with 2 arrowheads marked 3/7 going to R, and then one with 3 arrowheads marked 1/2 going to P, and so on. And then there will be other things coming from these, etc. And the number of arrowheads on a branch denotes the priority. So if you're at P, you first see if you can multiply by the fraction on the thing with 1 arrowhead. If so, you do so and go to what's at the end of that arrowhead. Otherwise, you look at the one with 2 arrowheads. So this is a much more convenient language than this official nonsense over here. Okay. So now let me show you a few programs to add some numbers. You see, what we do is we select a number of primes, which will usually be the smallest few primes, and the exponents of those primes are the numbers we're really thinking about. So I want to write a program that will add the exponents of A and B. So what do? Well, I just say, I come in. Oh, by the way, I forgot to tell you, one of the program lines is marked as being the starting line. And you indicate that by just putting a little arrowhead into it. So at line P, I multiply by 2/3 and go to P. And then if I can't do that, I multiply by 1 and stop. So yes, perhaps I should have indicated also that you can just have an arrowhead that goes nowhere, and that means when you get there, you stop. And you know, just for completeness, I'll put up a notional 1 on here. But you know, in fact, the simplest method is to have the convention. If ever you don't write a number anyway, it means you've written 1 there. Okay, so I hope you understand what happens to this. I multiply this by 2/3, and it's now 2 to the A plus 1, 3 to the B minus 1. I'm at state P in this diagram. And I still come back to state P. And then I'll find myself multiplying by 2/3 again. Until eventually I get 2 to the A plus B, 3 to the 0, and then I'm at the end. Then I can't multiply by 2/3 again, I'm finished. So this is a very simple little program that takes 2 to the A, 3 to the B, to 2 to the A plus B. Okay. Well, that wasn't such a very sensible program because it's sort of slightly destructive. It would really be rather nicer if I kept the original answers instead. So let me show you what I'm going to do now. Well, the first thing I'm going to do is clear register 5. That's because somebody may have been using this machine before me and they may have left something awkward in register 5. And now I'm going to copy register 3 into register 5. That transfers the contents of register 3 to register 5. You see, this makes the contents of register 5 0. And then this is just as we did before, it adds register 3 to register 5. Then, when you finish doing that, in state R, I want you to do 6 over 5. Now, let me just illustrate what happens here. Here we have 2 to the A, 3 to the B, 5 to for something horrible. Because, as I said, somebody might have left that in the machine. By the time we come out here, we'll have 2 to the A, 3 to the B. Okay? By the time we come out here, we'll have 2 to the A, 5 to the B. And now we multiply by 6 over 5 repeatedly. So by the time we come out of there, we'll have 2 to the a plus b, 3 to the b. Okay? So 5 to the 0. You know, we are always sort of ecological and clean. We always leave the 5 register at 0. But we can't sort of guarantee what our neighbours will do. So what that is a non-destructive adder. It takes what's in the 3 register and adds it to the 2 register, but it keeps it in the 3 register too. Now, the reason I wanted that is because now I can do this game to it. So what happens here is you subtract 1 from the 3. Oh no, I'm sorry, I don't want to do that. I want to do it from the 7 register. I subtract 1 from the 7 register, and then if I could do that, I proceed to add the 3 register to the 2 register, and then I subtract 1 from the 7 register, add the 3 register to the 2 register, and so on, until eventually I can't do it. So what this does is if you start with 2 to the 0, 3 to the b, 7 to the c, it will end up with 2 to the b times c, 3 to the b, 7 to the 0. And then, you know, let's clear.
What do you want to split state S?
Sorry?
You just cleared the 7 register. You split state S to subtract 1.
Oh, I did the wrong thing. I'm sorry. I did entirely the wrong thing. I should have said 1 into 7. You subtract 1, you don't go back to S, you go to P. So you subtract 1 from the 7 register if you can, and then add the 3 register to the 2 register, and you repeatedly do that until you can't subtract 1 from the 7 register. Then I'm asking you to clear the 3 register, and so this program converts 3 to the B, 7 to the C into 2 to the BC. Let me now precede it by a little piece that does 21 over 2 lots of times here. And this then copies the 2 register into the 3 and 7 registers first, and then does what I've just done. And so here, if you start with 2 to the n, this will get to 2 to the n squared. Okay? So I hope you can see that this programming language is actually pretty efficient. I've just programmed here a calculation that will take you from 2 to the n to 2 to the n squared. And it's very easy to see that any computable function in any of the standard senses of that term can actually be computed by one of these programs. Okay? Now that's very nice, because a Fractran program that computes anything. In other words, you can start with 2 to the n and have some Fractran program and get to 2 to the f of n. And I've just illustrated this with n squared, but some of you might like to write a program that computes n factorial, or, you know, whatever. Fine, well, it's up to you. But you know, Fractran was too complicated a language for my taste, so I'm now going to introduce a lot of dialects of it. I'm going to introduce programs called Fractran n, 1 to each integer. And Fractran n just consists of all the n-line Fractran programs. Okay? But I'm also going to introduce Fractran n and a half, which consists of all the n and a half line Fractran programs. And what a half line is defined to be a line that you can never jump into. The only way you can use it is by being the starting line. So there'll be at most one half line. And now I'm going to start trying to prove that, in fact, a one-line Fractran program can compute everything. Can do anything a Fractran program can do. That's not quite true, and so I'll fail when I prove it. But you'll see that that won't make very much difference. So here's the game. I simulate what do I do? I simulate n at p by p times n, where p is a large prime. So in other words, what I'm going to say is I'm actually going to number my program lines, which come out as the nodes in these diagrams, by large primes. I'll say begin at 101. And I'm going to suppose that the programs I'm doing never use any of these large primes, the new primes. There are always many more primes available. So if, for instance, you had that, okay, I'll simulate this by 2/3 times 103 over 101, comma, 4/5 times 107 over 101. Okay? So wherever, if our working number in the original program was n, our working number in the new program might be, say, 101 times n. But then look what actually happens. I'll come to multiply by this fraction first, and that will just replace the 101 by 103 and multiply it by 2/3. And that's just what I wanted it to do. So, you know, and replace this by this, etc. The trouble is, this doesn't quite work. I mean, suppose there were a loop like that. Then I'd find myself multiplying by a half of 101 over 101, and unfortunately that cancels and it doesn't quite work. So this only works if there are no loops in the program. But that's okay. Whenever there was a loop, I just invent a new node and do that. I can always sort of break loops into two pieces, and then, you know, if the cost of having a slightly more complicated program to simulate, I can arrange there weren't any loops. And then this now gives a Fractran 1 program that takes p times n to q times f of n. I mean, you see, I'm supposing, let's suppose that this is a program that finishes at state q and starts at state p. Let's suppose that we arrange that the only place that this stops is at state q. You can always do that. If it would have stopped somewhere else, have an arrow going from that to state q instead, and use state q that you have. And so we can't, with a Fractran 1 program, quite manage to get n to go to f of n, but we can make, say, 101n go to 113 f of n instead, which is quite good. But now, we can follow this instead by 1 over q at the beginning of this, at the end, sorry, of this Fractran line, and then that will at least get the ending right. I'll divide by q. You only divide by q when nothing else will possibly work, and that's fine. So now I proved the theorem that given any Fractran program that changes, goes from n to f of n, there's another Fractran program that goes from p times n to f of n, where p is a large prime not mentioned in the first one, so to speak. Well, now we can make a Fractran 1.5 program that does this. The top line, which is the half line, just does p. Go to the full line. And the full line consists of all these fractions. You know, b over a, p, s, comma, dot, dot, and then 1 over q. All going to itself. So this is a half line, and its only function is to multiply the starting number by p, and then you never use it again. So you come in, use this line once to multiply by p, and from then on you refer to this line. So Fractran has this really rather amazing property that no matter how long the program you had for it, you could replace that by a program that's only 1.5 lines long. And a half line is really quite a minimal thing here. You just multiply by p, that's the only operation you do in this half line. Okay, so it should now be obvious to you that you can write a one-line fraction program that does almost anything, or 1.5 line if you want to be precise, that does almost anything. So you will now perhaps guess how I got that from. I wrote a program to compute primes. Of course, I did it pretty efficiently in the first place, and then sort of gradually simplified it down to this thing. You can even see some of the places where there was a single loop. You see, this 33 thing, if you were in state 11, I wanted you just to multiply by 7 over 3. Transfer the 3 register to the 7 register. But that's a loop. And in my simulation procedure, I couldn't do that. So I had to split state 11 into state 11 and state 29 in order to do that. But it's a fairly easy task, programming. Okay, so let me just tell you some of the highlights then. One of the things you can do as soon as you've worked out a logical programming language is to write down a universal machine. So I wrote down a universal machine. Well, actually, let me not tell you about the universal machine just yet. Let me tell you about my pi thing. One of the functions you might like to compute is the nth decimal digit of pi. So I wrote down I think it was a 38 fraction list. And the game here is you start this at 2 to the n and wonder what the next power of 2 is. And it's 2 to the nth decimal digit of pi. So pi, of course, is 3.1415926535897793238462643388, etc. So, for instance, if you gave it 2 to the 5, as its starting input, the next directory you'd see would be 2 to the 9, and that's quite a nice little program. But then comes the universal one. This one I call pi game. But then comes the universal one. What do they call that? Polygame. And that's 21 fractions, which unfortunately I can't remember the way I remember those 14, otherwise I'd write them down for you. But what they do is you start at 2 to the 2 to the n times some constant, and it might stop at 2 to the 2 to the f of n. I mean, if it does stop, then what it stops at, if it's 2 to the 2 to something, you call it 2 to the 2 to the f sub c of n. And otherwise you leave f sub c of n undefined. And then the theorem is that no matter what computable function you give me, I can, so to speak, look it up in my catalogue and find the catalogue number, and then this one list of fractions compute it. And I have those 21 fractions written down somewhere. So for instance, you might say the factorial function is my favorite, and I say, okay, well, that is the 77th function. Okay? It's not going to be true, I might tell you. And then you'd start at 2 to the 2 to the n times 77, and then it would stop at 2 to the 2 to the n factorial. And then you say, no, I'm telling a lie. Really, my favorite function is the nth decimal digit of pi. So I say, well, that's really number 771, nth digit of pi. Well, again, I'm lying when I say that's number 771. In fact, I remember that number 77 is actually the constant function 1. Okay? But I did write down the constant that makes my universal machine compute digits of pi. I wrote it down on half a sheet of paper. It looks like 3 to the 2 to the 101 factorial times 491 over 657 or something, plus 2 to the 101 factorial squared times something or other, etc., times 5 to the something times 10. And basically what actually is happening is these fractions in here are the fractions that just constitute a program to compute pi. And so the way I find the catalogue number is I work out a program in this language to do whatever I want, and then code it up into the experiments. This number, 101 factorial, is just chosen so that it's so big that all these denominators here divide it. Perhaps I better make 1001 factorial. And I actually wrote down the catalogue number, because of course it is in this form. I couldn't write the decimal digits of that out. I think this is interesting because what it does for you, you see, the old books on this sort of stuff, well, they're not terribly old, any of them, a few decades old, proceeded like this. They sort of told you that, anything had a Gödel number, and you could do such and such with it. But of course, the Gödel number for a familiar function would be too complicated ever to write down. Okay. And so on. And they do a whole lot of things like this. And my aim was to improve the programming language until it got to the point where you could write down anything. So now, any function for which, any function you like, I can actually tell you the constant that does that function. I can write it down. And so there was some point in doing this. I took a very complicated function, the thing that computes n to the digits of pi, and actually worked out a program to do it. And it's quite a simple little program, just a list of 40 fractions, 38 fractions. It sort of works. And I believe that this is a very good way of doing recursive arithmetic, as a fine art. You see, by keeping it into this language, the great advantage of Fractran is it's something that is easy to program. That's to say, it's easy to make it simulate anything else, because a number can always be decomposed into its 2 parts and its 3 parts and its 5 parts and so on, which is what you use. But it's also easy to make anything else simulate it. And a lot of the proofs in recursive function theory just consist of one thing simulating another. And so here we have something that just says, look, simulate me. It's easy to simulate me. And it's very easy because it only has one number. And the entire syntax of the program, you only need to mimic programs that just have one line. And a line is just a list of fractions. So it gets very, very easy to do that. Anyway, I think I better shut up.
Thanks very much for a stimulating series of lectures here. Are there any questions?
Could you tie in a little bit to the very first game you introduced? Remember you introduced a game that had to do with modular arithmetic, and you said...
Oh, yes. Well, now, if you actually think of what one of these fraction games is doing, let's think of the fraction game 2/3, a half. What's that do? Well, if your 6n plus 0, if n is common to 0, 1, 2, 3, 4, or 5 mod 6, what you do? If n is 0 mod 6, you replace it by 2/3 n. If n is 1 mod 6, you stop. If n is 2 mod 6, it's a half n. 3 mod 6 is 2/3 n. 4 mod 6 is a half n. 5 mod 6, you stop. So you see, this is a Collatz type game. Okay? It's, well, I've brought in the stop orders, which are a bit funny, but I mean, okay. The sort of Collatz format is sufficiently strong that it includes the Fractran form. Okay? And therefore, in general, Collatz games are undecidable, because I could be asking you for a program to solve an unsolvable problem, basically. So this theorem really does prove that that kind of game is undecidable. So if it doesn't tackle any particular one, that's the fact that I can design a program to be doing anything doesn't mean that the particular program that the Collatz game is doing isn't a decidable one.
Question back.
doesn't the fact that a 21 fraction universal program exists mean that you never need more than about that many to write anything?
Yes.
A shorter version of
Perhaps I should say, too, that there was a clever grad student at Cambridge when I was interested in this stuff, who actually took the problem of thinning down these numbers somewhat. Yes, well, first of all, what you say is true. You never need very much to do anything. I mean, you see, this 21 fraction game here is already undecided. I have an explicit list of 21 fractions, and the problem of whether this game stops at a particular integer is an undecidable problem. You know, some integers it stops, some it doesn't. But the problem of given an integer, does it stop at that integer, is an undecidable problem. So that's one of the sort of merits of the system that I was trying to sell before. You get these undecidability results much more concretely than you used to. But then I should talk about John Rickard's improvements. He found a universal fraction game in either 9 fractions or 7 fractions. 7 fractions if you want 2 to the n to go to 2 times constant to go to 2 to the f of n. And 9 fractions if you want to do what I just did and make 2 to the 2 to the oh, sorry, I had to do one more round. 9 fractions if you want that, and 7 fractions if you want to do the other thing. And he also proved that 3 fractions isn't enough. However, Rickard's fractions are so complicated that you couldn't write them down. I mean, what he does is very, very clever. He takes a program that uses a certain number of fractions, and you know what you're really doing is any integer is of the shape 2 to the x, 3 to the y, 5 to the z, and so on, where this point x, y, z is an integer point with non-negative coordinates. And so you're really, of course, just jumping around in a room which is the first orphant, that's to say x, y, and z are positive orphant, with the rule being that you add first this vector if that keeps you in the positive orphant, otherwise this other vector, otherwise this other vector, and so on. Rickard found a clever way in which if you have such a program with n fractions that works in the positive orphant, with just n plus 2 fractions, you can make it work inside any polyhedron region at all. And then he sort of programs the polyhedral region. So it was very, very funny. It's like sort of taking this room instead of the positive orphant. Only imagine that it's infinite somewhere. It's quite incredible. And what you do is throw a ball around and it bounces off the walls. And he programs the walls so that, you know, the shape of the room, in other words, so that it can be fixed. And none of that enters into the number of fractions. And in this way, he got it down to 7. But his individual fractions will contain more decimal digits in their numerator and denominator than you care to think. You know, say 10 to the 10 to the 10 digit numbers, top and bottom. So you can't actually write them down, which is a proof that there exist 7 fractions, which make the universal game. My 14 fraction prime generator, I had another graduate student, though John Rickard wasn't a student of mine, by the way, but anyway, I had a graduate student at Cambridge who, the day he left, I met him in Sainsbury's supermarket at the checkout line, and he produced a tiny little piece of paper from his pocket, and it had 13 fractions on it, and he handed it to me. And I didn't say anything, but I presumed that was 13 fractions of complete primes instead of 14. Then I lost that piece of paper. And, you know, it might not have been right, because these programs often have bugs in them, perhaps more often than other programs, I don't know. But the version of Pygame that I put in my paper on this subject has a bug. It's really infuriating. It takes a fantastically long time, I may say, to compute the n integers of pi. If n is 1, it was all going to be. Compute the digit after the point. It would take, you know, it would still be computing long after the universe has gone cold.
Nonetheless, theoretically, it can be still. But the version I had in the paper that I first published actually carefully computes the nth digit for pi and then rubs it out. It's this enormous thing, and it actually always produces the answer 0, so it doesn't behave like that. And I sort of didn't notice that. I wrote the paper up in a tremendous hurry. In fact, the constant that I derived from it that makes the universal thing compute digits of pi is still accurate. And you know, you just change one of the fractions or something and make it right. But these things, it's very easy to have bugs in them. And so I don't really vouch for anything other than the ones, you know, I write down, so to speak. I did play for a very, very long time with the 21 fraction universal game. I found out what functions each of the numbers less than 1,000 computes, for instance. And you see, theoretically, that should be, so to speak, undecidable whether two integers compute the same function. But at the beginning, they're all quite easy.
One more question, and after that, people can thank the speaker, and people want to ask further questions, please stick around.
What was the sort of complexity of that range of functions?
Very, very simple. There's, you know, you don't realize this when you sort of come into it. You think that a simple function is, say, the identity of 0 function, or n plus 1 or something. But there are many simpler functions than those. For instance, the nowhere defined function. And then the function is defined only at 0 where it takes the value 0. Well, now you can generalize those to functions defined only at, say, 57 where it takes the value 93. Well, lots of the starting functions are like that. You don't get anything. I think you get the identity function in the first 1,000. You get the constant function 0 and the constant function 1 and maybe the constant function 2. You get the function that's defined everywhere. Yes, you get the function that's the identity function, except that it's not defined as 0. That's one of the possibilities, and so on. But then I wrote down I found the first integer, I believe, that gives the successor function, and it's something like a 4-digit integer. And then the first integer that gives the predecessor function. Okay, so I can't remember whether I asked it to be defined at 0 or not, but at n plus 1, its value is n. And that's about a 5-digit integer. And then, just for fun, I wrote down some other functions like n squared and so on, which you can do in, you know, sort of 10-digit integers. But as soon as you're prepared to allow integers like this to be written down, in other words, you measure the size of an integer by the amount of paper you can write it on, taking exponential notation into account, then essentially any function you like, you know, you can write in about a page. I mean, as long as it's not an absolutely crazy one. I mean, it would be entertaining, for instance, to yeah, it would be entertaining to do all sorts of things.
John, thanks very much.
Oh, yeah.